So I'd like to welcome Yasser Tahidi, is an electricity market specialist at ENTSO-E, working within the adequacy team in the system development section. In this role, Yasser is responsible for building pan-European techno-economic models for long-term planning and adequacy assessment, with primary focus to the European resource adequacy assessment. With a PhD in electricity market modeling and design, Yasser brings expertise to the team on development of robust and efficient electricity market frameworks, ensuring the reliability and sustainability of electricity supply across Europe, and addressing the critical challenges in the energy sector. Please show your appreciation to Yasser.
Hello. My name is Yasser Tahidi. I work at ENTSO-E. In this presentation, I'm going to introduce ENTSO-E a bit. What is ENTSO-E? What's our company? I will then introduce what is ERAA. Probably you are familiar with both. And then I will focus on flow-based. Maybe you are less familiar with that because this is a methodology for modeling network. It's specific to Europe. Maybe if you will not enjoy that part, I hope you will get some ideas about European electricity market, or if you are here to know more about PLEXOS, maybe you will learn some modeling, let's say, tricks that we do in PLEXOS in order to model to model the network by flow base in our ERAA model. So nothing special here. I will directly go to ENTSO-E. So ENTSO-E stands for European Network for Transmission Operators. It's an organization that encompasses TSOs of Europe. The aim of ENTSO-E is to promote cooperation between TSOs in Europe, also to make sure that energy targets of European Commission is fulfilled, especially in terms of renewable integration and also security of supply. What else? So you can see here some numbers that is relevant for ENTSO-E. So it's a big power system with 3.6 terawatt-hour generation per year, about 140 gigawatt of generation, 480,000 kilometers of transmission grid, and it serves more than 500 million people. Okay, this is an integrated electricity system, electricity market, and ENTSO-E is working on different aspects of electricity market in Europe, in terms of regulation, in terms of legal matters, in terms of network codes, in terms of security of data, and also what is the focus of this presentation and the focus of my work, the focus of system development section at ENTSO-E, which is on looking at the long-term, looking at the future, and basically do system planning and help policymakers, decision makers in European level investors to inform them about the situation, about the future of the power system, and also inform policymakers if it's needed to amend regulation to facilitate some changes and to amend some policies in order to make sure that the European electricity system reaches its targets and security of supply is ensured. Yeah. Okay. What is ERAA? So ERAA is a product of ENTSO-E. Of course, ENTSO-E is, as I said, it's an organization collaborating with TSOs. So when I say product of ENTSO-E, you can already, you should understand that it's TSOs. I have a lot of colleagues from different TSOs, European TSOs, that are part of this project, that we work directly, more or less together. So what is ERAA? ERAA stands for European Resource Adequacy Assessment. At ERAA, we look at 10 years ahead. We first defined a storyline. So we first defined, this is basically, it's the most important scenario here is the national trends. So what we get as from TSOs from each country, their best estimates about the future of the system. That is collected through a pan-European market modeling dataset, PMMDB. And then we have PECD. This is basically the forecast of weather scenarios, climate scenarios of future, considering climate change. In addition to that, we have network, which is the focus of this presentation. And also we have economic input. It's important to mention here at economic input that this is in fact an important part of ERAA because we are not just analyzing the data as they come through TSOs through PMMDB. At ERAA, we basically review again the economic viability of units and basically form another scenario which is on top of, which is after doing this economic viability check on top of the data that is received from TSOs based on the economic data, and having all this data, and so the final product is loss of load hours and energy not served, which are the most important indicators of ERAA. These indicators are used most importantly by decision makers, most importantly for capacity mechanism. So this capacity mechanism is an additional aid, let's say, that can be given to the supply side in order to make sure that we have adequate system. ERAA is not the only. Okay, so this is just a chain of just a loop in the chain of other regulations, other stuff that needs to be complied in order to have this capacity, to apply for this capacity mechanism, let's say. But one of the most important studies that the national studies also should be come hand in hand with that is European Resource Adequacy Assessment, or ERAA. We have different tools. We benchmark ERAA with different tools that can do this, but our main tool, our reference tool is PLEXOS. that economic viability check. So this is the long-term planning for the generation side to see if they're viable or not. This is also done using the LT plan of PLEXOS. And the part on a stochastic part on running the model on different weather scenarios, different series of force outage patterns. That's also done on PLEXOS, using both MT and ST schedule parts. Okay, so this is ERA. So from here onward, I will focus on flow-based. So what is flow-based? So, well, electricity, European electricity market. As you can see on top right, this is how the European electricity market is formed. So you see there are basically each country is a bidding zone. Some countries are more than one bidding zone. So the offers, supply and demand offers, when they come to electricity market, they come together from each bidding zone. And then it's important to set the transfer capacity between these bidding zones. And so far, it has been based on NTC. It means that the TSOs agree on the safe, let's say, capacity, exchange capacity between two countries. Here I'm trying to show you an example. So in this case, the limit of the lines, let's say, connecting these two are 1,000. But in net transfer capacity, you cannot put it 1,000, because if you just put every line 1,000, then from bidding zone A, you should be able to inject 2,000, and then, of course, the network, the physics of the network will send more than 1,000 through the connections. So that's not good. So that's why you have to define a little bit lower net transfer capacity. In this case, in this example, 750. But if you model the physics of the network, of course, you can make that higher, and finally you will be able to get the net position of, in that case, the bidding zone C cannot have more than 1,500 net position, but in the case that you model the network, it will be 2,000. The net position, the maximum one can reach 2,000. So in terms of how it looks in a graph, you can see that the area, when you model the physics of the network, instead of NTC, it's a bit extended. You can use your network better, more efficient. And what does, so how do we model this? It's of course, let's say, a simple DC power flow. So finally, you can basically represent your network through a bunch of constraints here. As you see here, so each line is each row is a line, and finally you have the PTDF matrix, which says that 1 megawatt injection to one node, how much of that goes to, based on the physics of the network, goes to each line. So, okay, that's not very complicated, but the complications comes when you consider that it's a bidding zone. So each country is one bidding zone. So you cannot put this constraint completely for the whole grid. You have to do something. You have to represent this in a zonal way. in a zonal system, and that's why it's called flow-based, and that's why instead of lines we have critical network elements and contingencies, and that's why in terms of simply thermal capacity of the lines, or F max, let's say, we have in this case RAM, or reliability, remaining available margin for each critical network element and contingency. I will go a bit more detail onto that, but anyways, finally, each of these rows are one constraint for that is finally appearing in the model, right? Okay. All right. A little bit more detail. I will briefly mention this. If you are using flow-based, or planning to use flow-based, it's maybe interesting to you. So the first, so as I said, the most important thing is that to basically represent this nodal DC power flow that you would like to have into a zonal form, let's say. So first, you need to put the market outcome, market set points from quite a variety of different situations in order to make sure that different situations in the network are represented in this market outcome. So here, in this case, we use, for example, the PLEXOS result of let's say previous simulation, previous year, previous era. We read so from one side, this is the data, and from the other side, it's grid. But okay, this market set points are zonal outputs because they're coming from market, and market is zonal. So you have to basically map those results into your into the grid in order to form a nodal model. Okay, then you basically can take a load flow and these nodal models. You can have your PTDF calculation. In order to translate this PTDF calculation into, well, this is a nodal PTDF. To put it into zonal PTDF, this is done simply through generation shift keys, okay, which basically translates what's the proportion of importance of each node when you consider a zone. So, for example, if there is a big generation in that node and it's generating, so the weight that you will give to that specific node when you want to represent it in your zonal PTDF is higher. So you put a higher generation shift key. So there are different implementation pathways there. So I will not go through that. An important element here is clustering. So in the long-term model, when you want to put flow-based domains into your long-term model, you cannot put it for each hour of, for example, 10 years ahead. You want to put for each hour a different flow-based domain. It's not possible. So you have to reduce that in terms of the data that you are dealing with. It's huge. The PTDF matrix is very big. So we do a clustering here, and how we do it, we look at the flows on most importantly, the flows on cross-border lines, and based on this, the flows in all the different market outcome that we considered, and we took the load flow, we select a good amount, okay, based on mathematical clustering approaches, some number of domains for summer, and some number of domains or representative hours, let's say in this case, for winter. Okay, of course, always when you do clustering, you need to train a AI model in order to use this AI model later when you want to allocate this well, in this case, X summer, Y winter domains. When you want to allocate, of course, then you need to use this AI tool again in order to allocate. So anyways, the final product is the thermal capacity of the lines. Okay, not so, not like that. You need, there are some elements that needs to be deducted from this, from Fmax of this cross-border lines, let's say. Okay, I will not go through detail. They represent the reliability margin, the situation without commercial exchanges, etc. Anyways, finally, you have your zonal PTDF, and you have your remaining available margins. So a bunch of constraints, let's say. And that's how finally the network, that's how finally you have the representation of the network using flow-based domains. What do I have? Okay. A bit, maybe an interesting trick here, and that I will briefly explain. So inside core, we have HVDC lines. So these are controllable, right? So these are a bit different than other lines. So how we deal with them, as you can see in that picture, we just, for each HVDC line, we just create a virtual system, a small system, just with three nodes that we just want that some power flow is turning around, because we just want to know the effect of flow on the total PTDF domains, as you see in the third element of left-hand side. Okay, the first element is the PTDF multiplied to the net positions of the net position of each bidding zone, plus what is coming from the connections outside the region that you are doing flow-based for, plus this part that I just explained for HVDC connections that we call it evolved flow-based. Okay, so your calculation of your PTDFs were originally based on the net position, the total net position of each bidding zone. But as you see in these pictures, the net position is in fact, if you just disregard NTC, let's say everything is advanced hybrid coupling, so let's forget about that part. But anyways, the total net position is the net position that is sent to your region, to the core region, the region that you are doing flow-based for, minus the part that's coming from outside. Okay, so there needs to be some recalculations there, but anyways, after doing these recalculations, you have the final constraint. So yeah, just a little bit of how it looks in terms of mathematics, and also importantly that trick about HVDC connections. All right, for PLEXOS modelers, I would like to conclude this. So I didn't show you any input or output of ERAA. If you are interested, you can find it at ENTSO-E website, the previously published ERAA 2023, which is also approved by ACER, the European regulator. Also, you can find the recently published ERAA 24, which is under review by ACER. So in that, you can find all the different input data that I explained, and also you can see the indicators and all the outputs in terms of economic viability of the system, etc., in that report. So here I just conclude with how what I explained about flow-based, how it finally shows in a PLEXOS model. So as I said, we have a bunch of constraints. So here I put the Nordic case, just an example, just to maybe show you that this part in the European electricity market, we have two flow-based regions. So one is core, consisting of central, western bidding zones. And also we have one part. So what I explained in the previous slide was all core. But we have also a separate group dealing with that with Nordic, with more or less similar methodology, not completely, but yeah, anyways. So that's also the same there. So as you see here at the end, we have a bunch of constraints, one constraint per each connect. And to each of the constraints, you associate the coefficient of the flows on advanced hybrid couplings, so the connections to outside core. You also have the what is sent from each bidding zone to the core, in this case to Nordic, so to the flow-based, let's say, region. And finally, the coefficients for HVDC lines also are considered in this constraint. And as you see here, for each of these three connections that we formed for each HVDC line, we just read one of them, one, because we make sure that there is no generation, there is no load, so each power, the power through this loop is the same for all of the, that is turning, so it's the same. So you just need to read one of them. And the effect of this flow through HVDC line implicitly shows itself through the net position of the bidding zone. If it's limiting and if it makes it a bit larger, if you send some flow through this HVDC lines, this will make it bigger so that you can have, let's say, higher net positions for Germany in this case. But anyways, just putting this constraint, reading this flow and adding that to this constraint does the job. And the net position of Germany will see that directly. Okay. That case that I just explained, the HVDC one, you see, in this case, this is for Allegro, the HVDC line between Belgium and Germany. We define 3 nodes for this and 3 lines. And as you see, only the coefficients of the first one is in the constraint. The coefficients of the second one, it does not appear anywhere. Okay, maybe an interesting trick. Of course, you can also consider it as just a direct connection between 2 bidding zones, but this mathematical formulation that I showed you becomes a bit more complicated if you want to put it directly in PLEXOS as a connection, not as a separate 3 node like this. Okay. All right. Yeah. Another good thing in PLEXOS worth mentioning here for some models, as I said, you cannot have PTDF and RAM for each hour of your simulation. You have to cluster, all right? And then you have to, after training this AI model, then you have to basically allocate each domain to each hour, all right? For this, very good, how to say, yeah, a facility that you have at PLEXOS is called time slices. And in using these time slices, so this is 3 summer, 3 winter domains with different PTDFs for each, for a certain connect and certain net position of Austria in this case, and also for RAM. You have different RAM, meaning a valuable margin for each domain, okay? Using time slices, you can easily, as you see, just put time slices in the columns of your input data, and then in the time slice, whenever a certain domain is selected, yeah, you see like that. So it makes it very easy to put this in your PLEXOS model. Yes, that's it.
Yes, sir. Thank you very much. Now, normally I'd say, is there any questions? But because Yasser has used every single second of his amount of time, I don't think we're going to get any time for questions. But we'll send a snapshot of his face out on social so you know exactly who he is if you need any questions over a coffee. Yasser, thank you very much for your time.